Welcome to the next part of this annotated reading of Introduction to Nanoengineering. This is nanoengineering at the center of it all. All areas of learning are interconnected. You can't have chemistry without physics, and you can't have biology without chemistry. Although nanoengineering is a new field, it stands at the intersection of several disciplines that we are already familiar with. The significance of learning about nanoengineering early, or really at any point in your education, is that it allows you to visualize how the knowledge acquired in other classes manifests in the real world. It also represents the forefront of nearly all fields of engineering. Moreover, a considerable portion of the discoveries in basic sciences that result in commercially viable products achieve this through some form of nanoengineering application. For example, information processing using microchips with transistors made on the nanoscale, drug delivery vehicles for vaccination and cancer therapy based on nanoparticles, and composite materials for ultra-lightweight aircraft that incorporate nanofibers, and new materials for batteries and solar cells can only be understood through the nano perspective. When I was in high school, my beat-up loaner textbook, which belonged to the school, was titled Chemistry, the Central Science. Central, I wondered, relative to what? Apparently central in relation to physics on one side and biology on the other. That is, physics, with its focus on atoms, electrons, photons, and thermodynamics, underlies the rules of chemistry, just as chemistry, with its focus on bonding, reactivity, and interactions between molecules, provides the basis for biology. The biologist Edward O. Wilson described such connectedness between areas of science as consilience. Consilience literally means the, quote, jumping together, or ultimately the unity of knowledge. The chain of relatedness of scientific fields is often discussed in terms of a discipline and an antidiscipline. An antidiscipline is the discipline that comes before, that is, the field of learning that provides the foundation for the next field. For example, physics is the antidiscipline of chemistry, and chemistry is the antidiscipline of biology. Given that few universities offer degrees in nanoengineering, what is the relationship between nanoengineering and other, more established fields? Which fields provide the basis for nanoengineering, and which fields, in turn, does nanoengineering provide the basis for? How is nanoengineering related to the natural sciences and engineering, and what is the difference between similar-sounding words of nanoengineering, nanoscience, and nanotechnology? The antidiscipline of nanoengineering are certainly each of the, quote, big three of the natural sciences, physics, chemistry, and biology. However, the relationship between nanoengineering and the other engineering disciplines is different. It is not a linear relationship, but rather a convergence based on the scale of the physical system. See this figure. If I can get it in focus there. Okay, that's pretty good. Hopefully you were able to pause it if you're watching on the video. So, I no longer believe that chemistry can be considered the central science. I've instead come to believe that the field that is truly at the center of everything is, in fact, nanoengineering. Nanoengineering is the understanding and use of materials and phenomena that occur on the scale of around 100 nanometers or less. Implicit in the word, quote, engineering is the use of these structures for the benefit of society. Nanoengineering products appear in microelectronics, integrated circuits, medicine, nanoparticles for drug delivery, energy conversion, solar cells and batteries, and storage, batteries again, and chemical manufacturing and environmental remediation in the form of catalysis. Nanoengineering exists at the frontiers of most traditional engineering disciplines. Certainly, chemical, mechanical, electrical, and biomedical engineering in two distinct senses. The first sense pertains to the size scale. When structures considered by these kinds of engineers are shrunken to dimensions of 100 nanometers or less, they are best viewed through the lens of nanoengineering. The second sense involves the exploitation of new physical effects to solve problems in the real world. Classical engineering, based on the laws of Newton, work effectively when treating objects as if they have no internal structure. Consider a block on an inclined plane from high school physics. In this scenario, the simplification of the block and the plane as solid objects with no internal structure works very well for objects that you can see with your eyes. Indeed, much of what needs to be known about mechanics and material science to produce, quote, macroscopic goods, for example, bridges, automobile engines, dishwashers, and radar antenna, is already known. On the other hand, the frontier of research in these areas, which are likely to uncover new physical effects and thus technologies that could transform everyday life, lie at the nanoscale. Okay, that was section 1.1. This is section 1.2. Nanoengineering, nanoscience, and nanotechnology. There is often some confusion among students and professors regarding the terms nanoengineering, nanoscience, and nanotechnology. Our working definition of nanoengineering is the development and use of materials and systems whose properties are derived from physical effects that occur when matter is constrained in one or more dimensions to 100 nanometers or less. The study of these physical effects, driven not necessarily by application but by curiosity, is nanoscience. Finally, devices and commercially sold systems that are the products of engineering are examples of nanotechnology. We regret if there are likely instances of these terms in this very book which do not align very closely with these definitions. For these instances, we are sorry, but only a little. Nanoengineering in a flask versus nanoengineering on a wafer. Now is a good time as any to admit how controversial the above definitions of, quote, nano are, even among people who work in nano throughout their day. Indeed, words with this prefix mean different things to different people. These differences have led to some comical interactions in my journeys as a professional nanoengineer. For example, it is very common for professors to make a few trips per year to different universities to give talks about their research. During this type of trip, the speaker visits with multiple faculty members in their offices to discuss researcher education or merely to reminisce about old times. During one such visit several years ago, a professor I had never met was adamant that nanoengineering was simply colloid science with a new name. Furthermore, they asserted that there was nothing novel about nanoengineering and that it was merely a form of, quote, marketing, designed to recruit students to attract research funding. I found this point of view unsettling and bizarrely confrontational. My interrogator was correct that colloid science describes the forces between suspensions of nanoparticles, such as those found in paint, fat globules in milk, and nanoparticles containing mRNA vaccines, for example, that helped get us out of the COVID-19 pandemic. However, colloid science, as venerable and as important as it is only a part of nanoengineering. You see, my exposure to nanoengineering came from a completely different perspective. In my PhD research, I developed some techniques to make arrays of nanostructures with controlled dimensions. These structures were made on flat, two-dimensional surfaces for applications in chemical sensors, light filters, and solar cells. In this respect, my work is more akin to the fabrication of microchips than it was to colloid science. Nevertheless, I was so taken aback by the stridency of my interrogator that I could not articulate my views. Having served as a professional professor in a nanoengineering department for more than a decade, I now have a better idea of how I would have responded to my inquisitor, who was so sure that there was only one kind of nano. In fact, there are two kinds of nano: nano in a flask and nano on a wafer. Here are the two kinds of nano: flask nano and wafer nano. Nano in a flask is synonymous with colloid science, while nano on a wafer is akin to microelectronics. Flask nano is also closely related to chemistry. That is, in chemistry, you synthesize things in a flask. Chemistry becomes colloid science when the substances you synthesized assemble into particles and arrangements of particles in a solution. Wafer nano, on the other hand, is closely associated with electrical engineering. You start with a silicon wafer, pattern your transistors, capacitors, and conductive traces, and dice it up into microchips. The other way to think about this type of application is to take a circuit board and shrink it down to nanoscale dimensions. Flask nano produces structures in random locations in a flask or reactor, but it does so at high volume. In contrast, wafer nano produces structures in precise locations, but it does so at low volume. That is, in flask nano, you generate copious amounts of stuff in a three-dimensional soup made of chemical reagents, the ingredients, in a solvent medium, the broth. Usually, such particles are used as is in this liquid environment. That is, they are used in suspension, as in milk, a bucket of paint, or a formulation of a vaccine, all of which are in a liquid medium. However, if you want to deposit the particles you have made onto a surface, it is very difficult to arrange them into precise geometries. Doing so is often called deterministic assembly. In other words, you have very little control over where the final particles are arranged on a 2D substrate. In wafer nano, in contrast, you can make almost any type of 2D pattern on a flat surface, like silicon, think microchips, or glass. It is also possible to make 3D structures by building up layer upon layer of 2D structures, like laying bricks to make a house. Such control can be achieved with outstanding precision using a process called photolithography. Photolithography, in our opinion, is the most sophisticated process ever employed for the manufacturing of commercial devices. Such sophistication comes at a cost. A new semiconductor manufacturing facility called a fab has a cost in the billions of dollars. In any case, the products of flask nano and wafer nano are quite different in appearance, but the rules which govern their behavior are the same. For example, electrostatic forces, including van der Waals forces, which you might have remembered from chemistry class, partially determine whether you get a stable suspension of particles or a solid clump. At the same time, these forces are responsible for the stickiness of metals, ceramics, and semiconductors to each other in solid planar devices, like chips. Moreover, the optical and electronic effects of confining materials to the nanoscale dimensions are equally applicable to both, quote, flask and, quote, wafer forms of nanotechnology. For example, the nanoscale processes responsible for the fluorescence of semiconducting nanocrystals in a flask, or perhaps someday in the bloodstream, are the same as what happens in the diffuser panels in quantum LED or QLED high-definition TVs. Finally, the physical consequences of size confinement are ubiquitous. We will find many consequences of the fact that when the critical dimensions of an object approach the atomic scale, materials have a significantly larger portion of their atoms on the surface. That is, as objects shrink, the fraction of the atoms on the surface increases. The consequences of size confinement are profound. Consider the example of chemical reactivity. In solid catalysts with nanoscale dimensions, there are many more active sites for the chemical transformation than there would be if the catalyst were a big chunk with smooth sides. For applications in sensing, chemical and biochemical analytes can attach and detach more quickly from the surface of the sensing material if it has a lot of surface area relative to its mass or volume. Moreover, the signals arising from the binding and debinding of the analytes to the sensor material are produced more strongly and more immediately. All of these effects are common to materials produced through both flask nano and wafer nano, and thus all fit under the umbrella term of nanotechnology, understood by nanoscience and produced by nanoengineering. Section 1.3, Engineering Across Traditional Boundaries. Nanoengineering draws inspiration from and has an effect on essentially all areas of science and engineering. By learning about nanoengineering as an independent discipline and your native, quote, STEM language, you get to learn about all the good stuff first. That is, you get to take a supersonic journey directly to the frontiers of science and technology without the need to retrace the steps of centuries of work carried out by generations of scientists and engineers. For example, what required mechanical, chemical, and electrical engineers decades to incorporate into world-transforming technologies, for example, the strength of carbon nanotubes, the biocompatibility of lipid-based nanoparticles for drug delivery, and the light emission from quantum dots, serves as the starting point for nanoengineers. Purists will say you have to learn the fundamentals first, and you will learn them. But asking a nanoengineer to get all the way through a physics, chemistry, or engineering degree before learning the good stuff would be like asking a sociologist to learn first everything about neuroscience and psychology before the first semester of sociology, which is normally undertaken the first year of undergraduate studies. So you can learn sociology right off the bat, just like you could learn nanoengineering without having to learn neuroscience and psychology and economics and then learn sociology. So we're skipping to the good stuff. All roads lead to nano. When we started the Department of Nanoengineering at UC San Diego in 2007, although I should say that I've since moved to the beautiful University of Rochester with the Genesee River behind me on this beautiful day. When we started the Department of Nanoengineering at UC San Diego in 2007, we recognized that the frontiers of most engineering fields lay in nanostructured materials. Consider a few examples. Microprocessors in which the transistors have dimensions of less than 10 nanometers, composite materials for aircraft which incorporate nanocarbon fibers, lipid nanoparticles for the delivery of mRNA vaccines, and display technologies utilizing semiconductor nanocrystals, i.e. quantum dots, for increased vibrancy of the images. Ask yourself, at what point in an undergraduate curriculum did the individuals who engineered these marvels of technology learn how to do this? The answer is nowhere, or at least not necessarily in a classroom. They learned how to accomplish these feats on the job or by accident. In this book, we will teach you how to, quote, skip to the end. That is, learn how to arrive at the frontier of science and engineering without having to earn a degree in a discipline which is only somewhat related to what you want to do after graduation. That is the power of nanoengineering that we are going to share with you. Section 1.4, Traditional Science Disciplines. The traditional science disciplines, sometimes called the natural sciences, include physics, chemistry, and biology. Just as biology is linked to physics through chemistry, nanoengineering is a product of chemistry, understood using physics, and often has applications in biology, or at least the biomedical sciences. Physics and nanoengineering. Nanomaterials derive their unique properties from their small sizes and the physical effects that result from this confinement. These effects often arise from the fact that a material sample with nanoscale dimensions has a large fraction of its atoms on its surface. The atoms at the surface have unsatisfied valencies, or bonds that they could form or would like to form, but have not done so. Visualize molecules at the surface of a thin puddle of water. When these surface molecules look up toward the air, they find that they lack stabilizing electrostatic interactions with other molecules like them. That is, they are deprived of around half the bonds that are experienced by atoms deeper in the bulk of the material. Effects arising from the missing interactions of atoms or molecules near the surface give rise to several properties of nanoscale materials. Such surface-associated properties include greater chemical reactivity, lower surface tension for liquids only, reduced melting points for solids only, and other effects. Collections of nanoparticles also organize themselves into dynamic systems based on principles of electrostatics and entropy. For example, nanoparticles, just like gas molecules in a container, like to spread out. These osmotic or entropic forces give rise to a range of important physical effects that occur on the nanoscale, but have consequences that can be measured on the macroscopic scale. By macroscopic, I mean you can see it with your eyes. Matter, energy, and force. Matter is the substance of which all things are made. In turn, matter is made of atoms and molecules and can be found in one of three basic phases, i.e. solids, liquids, and gases, along with a few other kinds that are important for various reasons, for example, plasmas and supercritical fluids. The properties of matter depend not only on the properties of atoms and molecules, size, charge, etc., but also on the way in which these atoms and molecules interact. Forces between atoms and molecules, the so-called interatomic or intermolecular forces, are hugely important. These non-covalent bonds, and I mean bonds that don't share electrons, or that don't involve the sharing of electrons, are interactions that underlie biology, materials science, and everyday phenomena. For example, the strength of these intermolecular forces determines whether the molecules in a given substance will form a solid, liquid, or gas at a given temperature and pressure. Intermolecular forces, in turn, can be predicted by understanding the potential energies with which the atoms or molecules interact, but only if we know how this potential energy changes as the atoms, molecules, or nanoparticles get closer together or move farther apart. To illustrate with a familiar example, we know that the gravitational force is attractive because your potential energy increases as you climb a hill and decreases as you climb down. Indeed, we will learn that the numerical value of energy in the system holds no physical significance except in its relationship to a reference state. In the case of the gravitational potential energy of a system comprising you and the Earth, the energy of the reference state, you standing on the ground, is set to 0 by convention. In other systems, like those consisting of atoms, molecules, or nanoparticles, the reference state is chosen such that the interacting objects are as far apart as possible. And here is a picture I drew of reference states. In other words, the amount of force between molecules, nanoparticles, and objects is equal to the rate of change of the potential energy between them. Thus, to say that the potential energy of a system is less than 0 or negative, usually treated as favorable, does not mean anything unless we know what the energy was before that state emerged. That is, the before state, the state with all the atoms held apart at infinite separation at the farthest corners of the universe. This artificial reference state ensures that there is no energy of interaction at all. That is, the potential of energy of interaction is 0. Thus, by convention, this arrangement means that when objects are stuck together, their potential energy of interaction is a large negative number. Light and waves. One of the defining features of materials with nanoscale dimensions is that they interact with light differently than do materials with macroscopic dimensions. Such properties of matter at the nanoscale are a consequence of their physical confinement of electronic states, or the places an electron either lives or is allowed to live. In other words, the available energy and/or the physical locations which an electron may occupy when confined within a nanoscale structure. Interactions between light and matter are dictated by a branch of physics called quantum mechanics. Quantum, in this case, just means that quantities like energy, wavelength, frequency, momentum, and so forth can only have certain values and not others. This property is called quantization and means that properties can only have discrete values and not a continuous range of values. The interaction of light and nanoparticles is a branch of nanoscience called nanophotonics, which is the basis of many fields of physics and modern technology. For example, optical signals confined to optical fibers under the oceans mediate much of the transfer of digital information globally. Light-matter interactions can also be used to glean the properties, shapes, and energy of particles of matter. When a photon, a tiny particle of light, strikes a molecule, nanoparticle, or surface, one of many different things can happen. The photon may be scattered or absorbed by the particle, or it may pass directly through the particle. To a large extent, the fate of the photon which interacts with a particle of matter depends on the energy of the photon and the size of the particle. For one thing, as stated above, the size of the particle determines the energy that electrons which reside in the particle can have. The energies of photons that can be absorbed often correspond to the energy gaps between these energy levels for electrons, that is, the states in which the electrons can live. Absorption occurs when an electron gets promoted from a lower energy state to a higher energy state. Photons, which consist of oscillating electromagnetic waves, can transfer energy to these electrons. The size of the particles determines the allowable energies of electrons and thus which photons can be absorbed. When an electron falls from a higher energy state to a lower energy state, a photon may be emitted. This process, emission, can be either fluorescent, which is usually bright and instantaneous, or phosphorescent, which is usually dim and occurs over a long time. Think about glow-in-the-dark stars or stickers, possibly on the walls of your childhood bedroom. For nanoparticles made of metal, there is a special type of phenomenon called localized surface plasmon resonance, or LSPR. The LSPR involves the periodic oscillation, sloshing back and forth, of the loosely held conduction electrons at the surface of the particles. Particles that are highly symmetric, like cubes and spheres, exhibit an LSPR at only one frequency. However, those with oblong shapes, for example, like cylinders or grains of rice, exhibit two distinct LSPRs, one for the long dimension and another for the short one. Thus, if you can collect and analyze the absorbed, scattered, and emitted photons and plot the intensity as a function of energy, or equivalently as a function of wavelength or frequency, you can learn a lot about the size, shape, and composition of a nanoparticle. This group of techniques, collectively called spectroscopy, is among the most powerful types of research tools available to a nanoengineer, or a chemist, materials scientist, or astronomer for that matter. The power of spectroscopy is that it reveals aspects of the structure and the composition of a material, even if the sample is too small to see using a microscope. In this book, we will discuss many examples of the use of spectroscopy to elucidate, shed light on, pun intended, the structure of nanoparticles. Chemistry and nanoengineering. In order to engineer nanostructured materials, the initial step is to have the capability to make them. The ability to synthesize materials, including nanomaterials, is the realm of chemistry. That is why chemistry forms the basis of a significant portion of nanoengineering. For example, semiconductor nanocrystals, also known as quantum dots, metallic nanoparticles, and polymer nanoparticles are all synthesized using techniques common to chemistry. In fact, the manufacturing of microprocessors using Techniques such as photolithography was enabled by chemical inventions such as chemically amplified photoresists. Molecules. A molecule is a collection of atoms which are bound to each other in a precise 3D arrangement. The bonds between these atoms are covalent, meaning that they share electrons. What differentiates a molecule from any old material is that a molecule has finite extent and size, a few tens of nanometers maximum. Moreover, every other molecule of the same type has exactly the same structure and is therefore interchangeable. Due to the unique bonding properties of carbon and the ways in which it can bond with itself, the skeletal structures of molecules mainly consist of carbon atoms. Thus, the chemistry of molecules is synonymous with organic chemistry. Organic, i.e., carbon-based structures are so named because they are the basic building blocks of life. Proteins, nucleic acids, carbohydrates, fats, and other molecules like hormones and neurotransmitters are all organic molecules. Synthetic compounds like fuels and other combustibles, some pharmaceuticals, and plastics represent extremely important areas of industrial manufacturing of engineering, and most of those are organic as well. Organic structures, specifically organic nanostructures, are everywhere. Look around you, particularly the objects and surfaces of objects in your current environment. Whether you are in an office, like I am, classroom, library, desert, or beach, it would be challenging to find any object that is not made of or covered with organic or molecular materials. Even desert sand and rocks have a surface microbiome, the, quote, biocrust, made of many types of microorganisms, lichens, and fungi. As you are likely indoors, consider that the window, although its bulk structure is silicon dioxide glass, is covered with either polymeric coatings or adventitiously adsorbed, meaning that these molecules are not inherent to the material, they're adsorbed accidentally, so adventitiously adsorbed organic structures from the air, possibly even from your breath. Thus, the ability to engineer materials at the nanoscale requires, at the very least, a functional understanding of molecular species and therefore organic structures. Reactivity. Like all forms of matter, nanostructures are made from atoms and molecules and thus have the potential for reactivity. They are subject to change and can also be engineered to bring about changes in their environments. In the field of catalysis, which often uses nanoparticles or nanostructured surfaces of larger samples to induce chemical changes, reactivity is their primary function. However, sometimes it is necessary to create a nanoparticle and suppress its reactivity. For example, you would not want a nanoengineered drug delivery system to damage cells or internal organs. Knowledge of chemical reactivity also plays a role in the synthesis of nanostructures in a flask. Many tried and true methods for the synthesis of nanoparticles made from semiconductors, for example, silicon, cadmium telluride, lead sulfide, etc., and metals, for example, gold, silver, copper, palladium, platinum, etc., exist in the literature with procedures that are relatively easy to follow, so you could make them following a recipe. Like the wheel or the multiplication table, such methods do not need to be invented again. While this book will not cover chemical reactivity to the same extent as a course in organic or inorganic chemistry, it is important nonetheless to know some key aspects. Such instances will be covered in this book where appropriate, for example, in the sections on catalysis and the synthesis of nanoparticles. However, there will not be a separate section on reactivity. Biology and nanoengineering. Some of the most exciting potential applications of nanoengineering are found in biology or biomedical engineering. One only needs to consider the success of the mRNA vaccines against the coronavirus that causes COVID-19 to realize the impact of, in this case, nanoscale organic vehicles that deliver mRNA. Nanoscale drug delivery vehicles have been around for decades, but their sophistication is rapidly increasing. In the case of drug delivering mRNA molecules, the justification for using nanoparticles is manifold. For one thing, mRNA vaccines cannot function without a vehicle to deliver them into the bloodstream and to the cells of the host. One reason is that mRNA molecules are unstable and would be hydrolyzed instantly in the bloodstream if not encapsulated. Moreover, if they were encapsulated in some random particle, the immune system would recognize them immediately and destroy them. So, structures called lipid nanoparticles or liposomes, which have polymeric or molecular components, were engineered so as both to encapsulate the mRNA molecules and to target them to their appropriate cells. Biology, a proof of principle. Nanoengineers often draw inspiration from biology. Biological systems are full of examples of functional nanostructures. For example, molecular motors spin bacterial flagella, viruses are quasi-living nanoparticles, and geckos stick to walls using a mechanism that arises inherently from nanoscale phenomena, in that case, van der Waals forces. Although there was much hype in the 1980s and 1990s about hypothesized quote, molecular assemblers, little robots that put molecules together atom by atom, biology already accomplished this. For example, enzymes and ribozymes are basically automated nanoscale robots. These automatons can affect chemical reactions to generate molecular and nanostructures from simpler principles that permit such exquisite control over molecular structures by these natural molecular assemblers. My voice is getting a little bit tired as I'm not a professional audiobook narrator. We will pick up with Chapter 1 soon, where I will talk about the differences or relationship between nano engineering and other traditional engineering disciplines. Thanks, and see you next time.